name's Herb Buxton. I'm with the U.S. Geological Survey. I manage the Toxic Substances Hydrology Program. It's in what we call the Environmental Health Mission Area. It's a relatively new organizational construct from USGS, which gives us a chance to really emphasize on environmental health issues and reach out and coordinate with environmental health sister agencies, federal agencies. What I'd like to do today is talk a little bit about what USGS is doing related to endocrine disruption in fish particularly, but there'll be some significance to human health. I think that we're all concerned about our ecological effects, but we're also very concerned about how they may be affecting us. The USGS is a science agency within the Department of Interior. It's one of our primary responsibilities is to assess the quality of the nation's resources, including our environmental resources, our water resources, things like that. And so that's really the charge, the mission under which a lot of this research is being done. Great. What I'd like to start out with is acknowledging the partners. I'm only the representative here. The work I'm going to present is conducted by numerous scientists, many within USGS, and many partners at universities, state agencies, other federal agencies. This is a list of the key partners, but what you'll see in all my slides is little citations to references at the bottom. There's also a handout that you should have gotten outside that has a list of all the references of those citations and a quick link where you can just easily access the paper if you're interested in getting the paper. That's the documentation for the talk. Now let's talk about what endocrine disruption is. Endocrine disruption can have developmental, reproductive, neurological, and immune effects. The effects, even though they can be exposed at very early life stages, they can be the result of exposures, chemical exposures at very early life stages, they may not become evident until later in adult life or even in subsequent generations. The effects can occur because of exposure to extremely low concentrations of chemicals. We're talking about parts per trillion, nanograms per liter. If any of you are interested in and have any experience in the environmental fields and you hear us talk about concentrations of chemicals, we started with milligrams per liter and then micrograms per liter and now nanograms per liter. More than a decade ago, we didn't even think about looking at chemicals at these levels in the environment and couldn't measure them. Nope, not yet. Sorry. It's okay. And not just at very low levels, but at mixtures of chemicals. And I'm going to give you some examples of that. It's really important to understand here that this is not a chemical by chemical exposure situation. We're not talking about the effect of exposure to a single chemical. It's exposure to combinations of chemicals that can act in concert, additively, multiplicatively, antagonistically interfere with each other. I'll say more about that too. Fish. We're looking at fish because they live in the waters. They're really a sentinel. These are the kind of species that may be affected first because they spend so much of their time. And in certain environmental settings, they really can be impacted with long, prolonged exposures, chronic exposures to these chemicals, endocrine disrupting chemicals. And lastly, our current treatment technologies, our wastewater treatment technologies that treat wastewater discharge and also drinking water discharge are not really designed to handle chemicals, and certainly not at these levels. Now let's talk about what endocrine disrupting chemicals are. They're biogenic and synthetic. Biogenic means we make them in our body. So biogenic hormones, women make estrogens, they don't make testosterone. These are the female and male hormones. Animals make them. So there are biogenic hormones that can be released to the environment through wastewater treatment plants, animal feeding operations. There are synthetic hormones, like the active ingredients in birth control pills, ovulation inhibitors. These are made to act like estrogen. Some may even be more potent than actual estrogen itself. And then there are a lot of other chemicals, industrial, commercial, household chemicals that are released to the environment that can act as mimics or blocks. And the mimics tend to act like the hormone. The blockers or antagonists may interfere with the action of the hormone by filling the role of the hormone and keeping the actual hormone from being able to send a message in our system. These hormones are like messengers. And Tom is going to talk more about this, I think, so I'm just going to stick with with getting to the fish effects. Give me this. So I wanted to say a little bit about where these chemicals come from, so you know it's not just an industrial or a single source. Wastewater treatment facilities. That shows a wastewater treatment facility discharging to a stream. Many that make it through come through our homes, and everything that industries and everything else that discharge to wastewater treatment plants. Then they're deposited in a stream at one point. So in effect, by not removing some of these chemicals, we could be concentrating them and having susceptible environmental settings right downstream from where the wastewater discharges. Another complicating effect of wastewater treatment plants is that they have biosolids. This is the solid matter that's associated with wastewater treatment facilities, and biosolids can absorb some of these chemicals. So they can be removed from the water, but they concentrate in the biosolids. The biosolids are then land applied very often as fertilizers. And so there's another pathway to the environment through agricultural fields or fields that are used where they're used as fertilizers. Thanks. Septic systems are another one, another source. We use them in our homes. They discharge through to our septic system. They leak into the ground. Another source is animal feeding operations. You see a swine facility with discharge pipes for liquid wastes to lagoons. The lagoons often overflow. You see a large cattle facility there. There's a lot of animals in one place. And you see the manure being applied, because the manure is also applied, the solids is also applied as fertilizer, even the liquid waste in some areas actually. And so here's the pathways to the environment. And then we have our industrial discharge sources, which we're more used to. One of the things I want to say about the animal feeding operations also is for some compounds that may be endocrine active, we have to realize that all the animals in a facility may be treated with the chemical, so that it's either a growth promoter or it's offered to the cattle prophylactically to prevent disease because they're so close together. Yet every animal gets it, so that there's a much higher density of the chemical coming out in their wastes than when you think of humans that, say, for a pharmaceutical, how many take a certain drug, and then it's a much lower density. So the equivalence from animal feeding operations could be a significant source here. So let's talk about what we've seen in the environment through time. This is a graph of, this is a plot of the data that we've collected. That goes back over to the late 90s, of finding intersex in fish. I'll talk more about what intersex is, but here we're really talking about a gonadal intersex, which means that in the male, for example, in the male gonads, in where we should see testes cells, we see oocytes. We see female cells, female characteristics in the gonads of male fish. It's called effeminization or gonadal intersex. And it's a really strong indicator of the effects of endocrine disrupting chemicals, because certainly in many species we call them gonachoristic. They're either male, an individual is a male or a female. So when we start to see mixtures of males and females in these species that are gonachoristic, like the fish I'm going to be talking about, then we know that something external is having an effect on these fish, and it's demonstrated that it's these exposure to these chemicals. Okay, so this just shows you that we found about 30% of the sites we sampled across the country had evidence of this intersex. So we see it a lot around the country. Next slide, please. We also look a lot at chemicals that occur across the country. This is a map of atrazine that we've done in a study. Look nationally at the occurrence of atrazine. It's used quite widely as herbicide on agricultural crops. Atrazine is something we've been looking at for a while. We've seen it for a while. But more recently, we're really understanding that atrazine also can act as an endocrine disrupting compound. And so we're seeing that it's important for us to look more closely at these chemicals and at the levels that it could be active at, low levels that it could be active at. And so this is just an example of chemicals that, looking broad nationally, we see the chemical occurrence. And we need to start linking this back to the occurrence of intersex. Because just saying that intersex occurs and the chemicals occur together doesn't mean there's a cause and effect linkage between the chemical exposure and the adverse effects on the fish. Show the next slide. Thank you. This is just another example of some of the data that we're collecting, and this is for more emerging contaminants. There's an effort on our part to keep looking at newer chemicals that are getting into the environment. So almost a decade ago now, about a decade ago, we started looking at pharmaceuticals. People didn't think of them as chemicals of important with respect to their environmental occurrence or being contaminants. And now we know it's important to look for them. And now we've got the methods to look for them down at these very, very low levels. So over the last decade, we were able to collect about 7,000 analyses of those compounds across the country, and that's with the help of many state agencies. We have just enough resources to collect limited occurrence data in certain locations, and then a lot of state agencies chipped in and wanted more information in our area, and we're continuing to gather that information. Now, let me go back to this cause and effect. This is the next question. We see interfects across the country. We see the occurrence of chemicals that are considered to be endocrine disrupting chemicals across the country. We really wanted to know about the cause and effect relationship, and one of the most persuasive, if not the most persuasive study was conducted in the last decade, was done in an experimental lakes area in Canada, where a very small concentration of ethinyl estradiol, which is one of those birth control pills, an ovulation inhibitor, was introduced to the lake, control lake, a lake where the synthetic estrogen was introduced as a spike and maintained for a couple of years. And as a result, I'll use the very words of the authors, ultimately they found a near extinction of the fathead minnow population as a result of the exposure to this chemical. That's probably the most persuasive evidence of population-level effects. Here, the population of that species was impacted by exposure to that chemical. Next. Now I'd like to talk a little bit about a study that we've done, which we don't have the ability to place that chemical in the field environment and release it to the environment. But this is a circumstance that's very close to that kind of control. You need that kind of scientific control to really demonstrate the cause and effect linkages. So it's in Boulder Creek, Colorado, upstream of the city. It's right near Boulder, the Boulder wastewater treatment plant. Upstream of the city is very pristine conditions. You see the picture in the top left. Boulder's at the foothills of the Rocky Mountains. It's very, very pristine conditions. There are not many people, not many animals. Then there's a Lowhead Dam, which is very convenient because it separates the fish populations from upstream and downstream. And then downstream is where the wastewater treatment plant discharges to Boulder Creek. I put data on there for 17-beta estradiol, which is the biogenic estrogen, one of the natural estrogens that we produce in our bodies. And you see that it was below our detection level of 0.8 parts per trillion or nanograms per liter upstream, and you see about 2.9, 2.1, 1.2. You see it dissipate a bit downstream after it's introduced to the environment. Okay, can you see the next? Now remember I said that it wasn't just individual chemicals that we were worried about. Here what we did was look at a number of other chemicals that also are estrogenic, also have properties that make them act like estrogens. So we looked at ethinyl estradiol, which is that synthetic estrogen, 17-beta estradiol, and estrone, which are two natural or biogenic estrogens, and a number of other non-hormone endocrine disrupting chemicals, like industrial chemicals. Bisphenol A is in there, a number of detergent metabolites like norephenol, and its degradation products that all have some estrogenicity. And when you add it all up, you see what the effect of in the reference site, which is upstream, compared to in the effluent itself, compared to in the stream where the effluent is introduced. And you see now, remember I said in that experimental lake area in Canada, the concentrations were about 5 or 6 parts per trillion. Here you see how much higher we get when we add all the concentrations of all the different, not all, but just a subset of the chemicals that we think are the biggest players. Next. And what we see in terms of effects. This is 2 different years of studies. The graphs show the percentages of males and females, upstream versus downstream. You see in 2004 that upstream was about 60-40, and downstream the number of males is significantly reduced. You see the same effect in the fall of 2003. Click again. Intersex. Click once more. Now, intersex, again, I mentioned it before, is this evidence of female cells, female sex characteristics in the gonads of the male fish. And that's where a picture, evidence of it. You see the male cells, which are the ones that are slightly dark, here with dark dots in them, and these big round oocytes, which are the female cells. Those are different. That's the evidence of feminization of those male fish. So we went one step further, not just having evidence compared to upstream and downstream and using the benefit of a low-head dam, but we developed a mobile laboratory that we were able to put on site. The mobile laboratory, again, has the ability to take waters from upstream as reference waters and effluent and mix it in different dilutions. Through the year, as the stream flow changes, the dilutions change. And so, as an example here, I put a reference dose of 50-50 mixture and 100% effluent mixtures. And what we saw here was, it was 28-day experiments on fathead minnows. Within 7 days, vitellogenin is a egg yolk precursor. It's found in the blood of female fish, and it's not usually found in the male fish. In the reference fish, we found trace levels in the fish exposed, the male fish exposed to the 50 and 100% effluent. Within 7 days, they found elevation of the vitellogenin by 3 orders of magnitude. Also, there were primary and secondary sex characteristics that within 14 days were demasculinized. There are physical characteristics, things called nuptial tubercles, they're physical appearance of the fish that are used in breeding behaviors, nuptial tubercles and fat pads that are characteristic of males. They use them in the breeding process. These were decreased significantly in 14 days, and sperm abundance was decreased significantly in 14 days, not in the reference sites. So again, what we see here is evidence both in the field exclusively, where the fish populations are separated by the low-head dam, and then in a laboratory where we have about as much control as you can get and still maintain field conditions. Those waters are able to be piped through the lab at the right temperatures, all the other controls, photo periods, when the lights come on and off, everything else maintained as much like the actual environmental conditions as possible. Now what I just want to do is review what goes on here. And so since 2000, we've been studying at this creek the chemical loading, the characteristics of intersex, the demasculinization of the fish in the laboratory setting right adjacent to it, and a few other things that you have references to. What we're studying now is what's happened since 2007. In 2007, there was an upgrade to the wastewater treatment plant. The wastewater treatment plant was upgraded from trickling filter to activated sludge. What we have seen so far, and is written up now, and it has not been published yet, but preliminary evidence is that there was a significant decrease in the number of the chemicals, the estrogenicity of the water, and a significant improvement in the fish health. And so that paper is being written up now. We expect to be out in the next 6 months or so. So I want to go one other next step, and I want to take this to a field site that's closer here, but also has some more significance to much more complex environmental conditions. This is the Potomac River, where the interest started in 2002 when there was a significant increase in fish kills. What we saw was parasites, bacterial infections, fungal infections, exposure to contaminants, water quality, water chemistry kind of conditions changing, and all contributing to the fish kills. The fish kills were largely, you see that's a parasite on the gill material. So you see that what the actual cause of the death of the fish was probably the bacterial infections and fungal infections and parasite infections. But again, what we're also learning is that these fish also had gonadal intersex and evidence of exposure to endocrine disrupting chemicals. Used to seeing that slide again. There's the oocytes, the female cells with the spermatogenic tissue. Click again. Now, one of the effects, you remember I mentioned early on, of endocrine disruptors is interference with the immune system and potential immune suppression. And so right now, the scientist hypothesis is that it's the combination of stressors, exposure to the chemicals, that could suppress the immune function, the resistance to disease, resistance to other stressors in the fish, that's causing them to be more susceptible to these fish kills. Because in controlled settings nearby, you do not see the fish kills, you do not see the exposure to the endocrine disrupting chemicals, you do not see the evidence in things like intersex. So they're doing a very detailed study that allows them to look at all the factors of all these different stressors on the fish, all the different disease agents in effect, from contaminants, pathogens, parasites, fungi. And what we're left with now is trying to understand where the contaminants come from. There's a quite mix of land use in these areas. There are lots of different point sources, wastewater treatment plants, animal feeding operations. There are things like manure piles adjacent to the stream that could fill over into the streams during runoff. And so right now there's a paper that just came out August 4th, actually, that does a lot of work doing statistical relationships and try to understand which are the most important contributing factors. You can get a copy of that paper via the handout I left outside. Next. What I'd like to end with now is, what does this mean to us? I mean, there's a lot of very important work assessing the impact of endocrine disrupting chemicals on fish. As I said earlier, the fish live in the waters. They're in effect a sentinel. They're the type of species that we would expect to be affected early on because they live in the waters where many of these chemicals are. And they have continuous exposure in many cases. But we're also looking at the occurrence of many of these chemicals in drinking water supplies, in both finished, which is treated, and unfinished or source waters, before the drinking water is treated and after the drinking water is treated. These are just a couple of different examples of the types of studies that we've done. One is in public supply wells. You see 932 public supply wells from across the country, about 250 to 300 compounds studied, maybe even to 350 compounds studied in these studies. The other is almost 1,400 domestic wells. These are on-site wells where individuals have their own well right in their home, pump their own water in, don't have the benefit of a centralized treating facility like in public water supply systems. And so we're trying to make efforts to look at these chemicals more systematically across the country to give good insights into potential human exposure, because human exposure is really key. We need to understand which chemicals have the ability to have certain effects, have certain biological outcomes, and also what the level of exposure to those chemicals and the mixtures of those chemicals are. And really understand both of these is important to understand the relative threat value and the need for mitigating actions. Next slide. And one more about endocrine disrupting chemicals in drinking water. This is just a slide from a recent study we did. We're constantly trying to improve the coverage with respect to chemicals that we're looking at in water. This is a study of source waters in about 50 streams and 25 wells across the country. They're from small to large drinking water facilities at the intakes before treatment. And it just goes to show you the wide range of chemicals. Many of these chemicals are known or suspected endocrine disruptors. Right now we're doing a systematic assessment of the literature to identify chemicals that we feel have enough evidence to justify making them a priority with respect to our methods development. Methods development means we take them into the laboratory and we make sure that we can measure them at very low concentrations in environmental samples so we can go out and collect data like this and estimate exposure. And with that, I thank you, and I guess we'll take questions at the end.